So, today we're diving into something pretty amazing in the world of clean energy. It's a story about, well, it's about cooking with fire and how that simple idea might just be the key to unlocking affordable, clean hydrogen for all of us, all because of a huge 45% cut in a very, very expensive ingredient. All right, so first, let's set the stage. Why is everyone talking about hydrogen anyway? Well, think about it. We're getting really good at making clean electricity from the sun and the wind. But what do you do when the sun goes down or the wind stops blowing, right? You need to store that power, and that's where hydrogen comes in. It's basically the ultimate clean portable battery. You can use all that extra renewable power to make hydrogen, and then whenever you need it, you use the hydrogen to get that power back. And that right there, that's what we call the hydrogen dream. I mean, the whole idea of a totally clean energy loop is just, it's incredible. But actually making it happen, turning that on again, off again power from renewables into something we can count on 24/7, that's a massive, massive challenge. So, what's so special about hydrogen? Well, here's the magic trick. When you actually use it, whether you burn it or run it through a fuel cell for electricity, the only thing that comes out the other end is water. Just pure water. No carbon, no pollution, nothing. It's the perfect fuel, right? But, and there's always a but, there's a huge catch to making it in the first place. And that catch brings us right to the main problem in this whole story, what I'm calling the precious metal problem. Yep, there's one major bottleneck that's been putting the brakes on this whole hydrogen dream. And it all boils down to one single material that is unbelievably rare and unbelievably expensive. Okay, so the way you make clean hydrogen is called water electrolysis. It sounds fancy, but the idea is simple. You zap water with electricity, and it splits into hydrogen and oxygen. Easy, right? Well, not so fast. To do it efficiently, so you're not wasting a ton of electricity, you need a little helper, something called a catalyst, to make the whole reaction happen way, way faster. And here it is. Here's our villain. The absolute best catalyst for this job, the gold standard, is made from something called iridium oxide. The problem? Iridium is one of the rarest metals on the entire planet. Like, seriously rare. And that, of course, means it is crazy expensive. Trying to build a whole global hydrogen economy on iridium would be like trying to build every single car out of solid platinum. It's never going to work at that scale. Okay, so this is where things get really interesting. Faced with this impossible problem, a team of researchers decided to do something different. Instead of trying to invent some super complex, high-tech solution, they went the other way. They decided to literally cook up a new catalyst, using a method that's surprisingly simple. The method is called solution combustion synthesis, or SCS for short, and you can pretty much think of it like blacksmithing, but on a microscopic scale. You just mix your ingredients together in water, you heat it up, and then whoosh, it ignites in this super fast, self-sustaining little fireball. This tiny, controlled fire forges all the ingredients into this fine, high-tech ash. And the best part? It happens in one single step. It's super fast, super efficient. And get this, the recipe is incredibly simple. You just take your metal, which is iridium chloride, you mix it with a fuel and an oxidizer and some water, you warm it up a bit till it turns into this gooey gel, then you stick that gel in a hot furnace, and it just ignites. It literally bursts into flames. Once the fire dies down, what you're left with is this fine, black, spongy ash. And that's it. That's your brand new high-performance catalyst. But of course, the scientists didn't just try one recipe. They were like chefs in a lab, experimenting with different ingredients to see what would happen. They were trying to cook up the perfect catalyst. And in doing that, they stumbled onto one surprise ingredient that changed absolutely everything. So here's a look at what they were testing. They had three main candidates. The first one, called IRG, was just the basic mix. The second, IRMG, had an additive, ammonium nitrate. But it was the third one, IRALG, that was the real star. It used aluminum nitrate. And that one little tweak to the recipe, well, that was the breakthrough. Yeah, the winner by a long shot was IRLG. And here's why it's so cool. Adding that aluminum nitrate didn't just make the little fire burn a bit better. No way, it completely changed the physical structure of the final material. It created something totally new, with a shape and design that turned out to be incredibly powerful. And when you actually look at this winning catalyst up close, wow, check this out. It's not just some boring powder. It's this gorgeous, complex, spongy structure. It's made of all these tiny little needles that have kind of fused together into these almost like little sea urchins or starbursts. And all that complexity, that sponginess, creates a huge, huge surface area. Now, if we zoom in even closer, this is where we find the real secret sauce. That aluminum nitrate, it didn't just go up in smoke. It actually formed a kind of scaffold, an alumina support structure. And then, scattered perfectly all over that support, are these unbelievably tiny particles. We're talking 1 or 2 nanometers of the precious iridium oxide. This is the whole game. Instead of one big, expensive lump of iridium, you have these tiny, powerful specks doing all the work, spread out over a massive, cheap structure. It's like decorating a huge sponge with microscopic diamonds to get the maximum sparkle. So let's just recap. This winning recipe gave them everything you could possibly want in a catalyst. A massive surface area, that unique, spongy structure, and those perfectly spread out tiny little nanoparticles of iridium. It was basically the perfect tool for the job, cooked up in a single fiery blast. But of course, the big question is, how well does it actually work? All right, so it was time for the main event. They had to put their new lab-cooked catalyst to the ultimate test, a head-to-head showdown against the super expensive, top-of-the-line commercial stuff that's the current champion. This was it, the moment of truth. And here you have it. This graph tells the whole story. The simplest way to think about this is that being higher and further to the right is better. It means more bang for your buck, electrically speaking. Now, that green line, that's the expensive commercial champion. And the purple line, that's our new challenger. And as you can see, they're basically right on top of each other. They're identical. I mean, this result is just stunning. For a brand new material cooked up in a lab with a simple fire-based method to perform exactly as well as the super refined industry standard product, that's a huge win. But believe it or not, that's not even the punchline. So, what makes this a real revolution? Well, it achieved that same top-tier championship-level performance while using 45% less of that super rare, super expensive iridium. And that, my friends, is what we're calling the 45% revolution. Because, look, when you're dealing with one of the most precious materials on Earth, being able to do the exact same job with almost half the amount, that's not just a small step forward. That's a giant leap. It's a total game changer. Just let that sink in for a second. You get the exact same performance as the best stuff on the market, but you cut the need for that precious metal iridium by almost half. That is just incredible. So, why is this such a big deal? What does this all mean in the real world? Well, it means lower costs, which makes clean hydrogen way more affordable. It means we can actually scale this up and build the massive hydrogen plants we're going to need. And because the cooking method is so simple and reliable, manufacturing becomes a whole lot easier. Basically, this one breakthrough starts knocking down several of the biggest barriers to a real hydrogen economy, all at the same time. And that leaves us with a really powerful final thought, doesn't it? That a process as simple and, as ancient as cooking with fire, a tiny controlled flame in a furnace, could be the key that finally unlocks a truly affordable, clean energy future for every single one of us.